Hello, honors chemistry student. This is a supplemental video for y'all's lessons on bonding. Honors chemistry students have a couple of concepts throughout the course that we do with just y'all and we don't do with general. And this is the first one, so molecular geometry. We've been talking about how to draw Lewis structures and how to determine the type and number of bonds for a Lewis structure as well as the polarity of a bond. And for honors, you have one additional thing that you're going to need to be doing, and that will be identifying the molecular geometry. So molecular geometry is just a fancy way of saying what is the shape of the molecule around a particular atom. Now for our chemistry students, honors chemistry students, you do have a cheat sheet that you will be able to reference on quizzes and tests. It looks a little less funky than the one that's on the right side of the screen, but it does summarize all of the different molecular geometries that we will look at in this course. If you were to take chemistry in college or take AP Chem, you will notice or you'll learn that there's actually like double this, but we are focusing only atoms who either have an electron deficient cloud or have the octet. So to determine a molecular geometry of a substance, you're going to pick a central atom. When we've been drawing our Lewis structures, we've been doing simple Lewis structures that only have either one element, well, two elements total, or three elements with two around a particular one. So when we are trying to describe the molecular geometry, we are looking around at what shape does it make around that central atom, and that's kind of important to make certain you identify what your central atom is. So there are 5 basic shapes that we will look at this semester. First one is tetrahedral. It is probably one of the easiest to recognize. A tetrahedral shape requires 4 single bonds only. It has no lone pairs, it has no dots around that central atom, and it has 4 single bonds coming off of it. So in my little graphic, that A could be anything. It could be carbon, silicon, any element. We're just identifying that as a central atom, and X's could again be any other element. So chlorine, fluorine, hydrogen, anything. We don't typically show the lone pairs around the external atoms, those X's, because it does vary from element to element. But tetrahedral, like I said, is probably the easiest to recognize because it's got 4 lines coming off of it. 4 lines, no dots. Next is our trigonal planar. So trigonal planar has 3 bonding areas and no lone pairs. The most common trigonal planar that we will see is up here on the top right, where you have 3 single bonds. That's the one that boron almost always makes. Boron is one of the few elements who is an exception to the octet. He is electron deficient. So boron is stable with 6 electrons. Remember, we've already identified one electron deficient element earlier, and that was hydrogen, who likes having only 2 electrons to achieve stability. So a second one that's electron deficient that we will play with in this course is boron. The other type of trigonal planar has a double bond to one of those atoms. Boron does not do this, but other elements do. So it has a double bond and, bad misreads, 2 single bonds. So that's what I mean when I say 3 bonding areas. There are 3 areas around that central atom within which we have bonds, whether it be single, double, or triple. Our next one is bent, and depending on how you actually draw it on your page, you may not visually see that bent. But bent has 2 bonding domains, 2 bonding areas, and either 1 or 2 lone pairs. So there's actually 2 different versions of the bent. One version of the bent has a double bond with 2 lone pairs, and the bad misreads has a double bond with 1 lone pair. And the other version of the bent, which is the more common one we're going to see, has 2 single bonds and 2 lone pairs around that central atom. So when you actually look at it in three-dimensional space, it is actually got a bent kind of an L type shape. But when this top one, it's kind of hard to see that those X's are coming off of us out of the screen. Goodness. So next is linear. Linear has 2 bonding areas with no lone pairs. That is our most common linear. That involves more than 2 atoms in the molecule. So linear, there is actually 2 different types of linear. One has 3 atoms. It has 2 bonding areas and no lone pairs. Again, those bonding areas could be single bonds like we see in this top one. It could be 2 double bonds like we see in the one that I'm about to outline in purple. And I don't know why my little marker didn't want to go. There we go. Or it could be a single and a triple bond to get that linear shape outlining in light blue. So those are your main types of linear. There is another type of linear, and this is only with our diatomic elements. Diatomic elements are 2 atoms, 2 elements that are bonded together. There are 7 diatomic elements on the periodic table. They form a 7, starting at 7. And these are elements that do not exist in nature by themselves. So Brinkelhoff is one way to remember it, but I like the 7 in the shape of the 7. So nitrogen, oxygen, fluorine, chlorine, bromine, and iodine plus hydrogen are our 7 diatomic elements. And they always form a linear shape because they're just connected to their twins. So H connected to H. Has no choice but to be a straight line. O connected to O. Has no choice but to be a straight line. Last but definitely not least, trigonal pyramidal. So trigonal planar is one-dimensional. It is a flat molecule, where trigonal pyramidal does actually exist in 3 dimensions. And trigonal pyramidal has 3 bonding areas and 1 lone pair. 3 bonding areas and 1 lone pair, circling it on the right-hand side. That is what we are going to see for our first year chem. So let's look at a couple examples and see if we can use our little tool to determine what is the molecular geometry of a few simple Lewis structures. Before that, this is the most up-to-date reference sheet. I am not confident that it 100% matches the one that's on the printed version of the periodic table, but I know it is fairly close. So our 3 examples here, let's determine the shape around that central molecule. So what is the shape around my carbon or my boron in the 3 that are currently on the screen? And I think there's a 4th one that just hasn't shown up yet. So in my CCl4, carbon tetrachloride, that central molecule is the carbon. I can easily see that it has 4 lines coming off of it in 4 different directions. Therefore, it has to be tetrahedral. My CO2, carbon dioxide, again, the central atom. What is the geometry around that central atom? Well, we have no lone pairs, so we can rule out any of the ones that have dots around them. We've got 2 areas of bonds around it. Therefore, it must have linear molecular geometry. Oops, formatting issue. That 3 should be down at the bottom. So boron tetrafluoride, what is its molecular geometry? Well, boron is one of 2 electron deficient elements that we play with in first year chem. Boron is stable with 6 valence electrons. It has no lone pairs around it. Therefore, it must be trigonal planar. There's the last one. So last but definitely not least, this is a substance that we don't necessarily know how to name using our nomenclature rules. It's an organic molecule. I'm not going to get into all that. But we could identify the shape. So if we look at that carbon, we can see that there's no lone pairs. and there's 3 areas or 3 elements around it that have bonded, therefore it must be trigonoplanar. It's a version of trigonoplanar that has a double bond somewhere on it instead of just 3 single bonds. So why is molecular geometry important? Well, when you look at some of the bigger molecules, molecular geometry can determine how a substance will react in something else. So think about the pharmaceutical industry when they're trying to build these complex molecules to fight certain diseases or certain symptoms. So this, I don't remember what its name is, but it's a really big molecule, something that you're not going to be expected to draw for first year chem. But we could identify certain elements and see what is the geometry around that particular element. So first one I'm going to identify here is this nitrogen with this purple circle around it. Notice 3 bonds, 1 lone pair. So nitrogen with 3 bonds, 1 lone pair is trigonal pyramidal. That lone pair of electrons is kind of going to be above that nitrogen, forcing the other 3 to be a little bit below the plane on the nitrogen. Next one we're going to look at is the carbon that's on the left side of the screen. This carbon, notice it is bonded to 4 other things. It has no lone pairs, therefore it must be tetrahedral. It must be tetrahedral. Next one we're going to play with is this nitrogen down on the bottom right. Notice the nitrogen on the bottom right has 1 lone pair, but it has 2 areas of bonds coming off of it. 1 lone pair, 2 bonding areas must be bent, and you can very easily see that bent shape. And last but not least, one of the carbons on the bottom left. Carbon has no lone pairs, has 3 bonding domains, therefore it must be trigonal planar. So that means that nitrogens, or those nitrogens and that oxygen, they are all on a single plane. And what do I mean by that? Well, if we go to the program that actually made this drawing in, I can take and grab it, and we can see that when I look at it from a slightly different angle, there are things that are poking up above and below the plane where most of the other atoms exist. This is probably not 100% correct because these little gray balls that are attached to the blue would be slightly above or below because of the lone pairs, but it's the program that's the closest to what I have. Let's see if I can get it to show the $3D a little bit better. Okay, so yeah, that's as good as I'm going to be able to get with the Molly View. So last, big idea. No, and guys, gals, y'all are not going to be expected to draw something like this. This particular program does not show all the lone pairs. When we are doing our Lewis structures, I ask that you show the lone pairs on your atoms because it helps you make certain that you've got all of your electrons accounted for. So we will always show the lone pairs of electrons around our external atoms, however many they need to be. That is it for our molecular geometry supplemental. Remember, you're given that little data table, so you don't necessarily have to memorize. You just need to be able to match a illustration with the general shape that it forms.